Hello and welcome back to yet another episode of Learning Rust with Gadoxide. This is your host Sebastian and my co-host Sydney.
Hey guys, welcome back.
And what you see here is exactly what we ended up with the last episode at. So we have this variable x, or this binding x, that we declared the type for. So now we know it's holding exactly a mutable borrow of the number 42. So here's the number 42 and we borrow it mutably. This also means that apparently it lives here, because otherwise if you wouldn't own that, maybe it's a bit hard to get a mutable borrow of something. But since we do have it here, we can. And then we are adding one in place by handing over that borrow somewhere. Remember, this asterisk here is needed to dereference that borrow, and increment it by 1. And one line later, we are allowed to just print it with an immutable or shared borrow. And apparently, a mutable borrow can always create for you inherently, implicitly, an immutable borrow, which makes sense because if you can write something, you can definitely also read something. So there's no write-only thing in Rust. There's always write and read, or read only. I think that's a decent summary of what we see here. I don't know if you saw it, Sid, but there was a comment on YouTube that was, I think, clarifying a few things that might not have been very clear when we talked about it. And it gave me the idea. So first of all, thanks for that. Always welcome. Be invited to enlighten us with your knowledge in the comments below. But also, this led me to remember that there was more about this here. Because this mutable reference, like, is it something that you can just copy left and right and kind of have multiple versions of that around? Because then you kind of have multiple writers. And that's something that we said Rust is preventing actively. And I think the easiest way, do you have a way in mind that we could put that to the test with? How can we test?
Well, you would try to make a second variable of it, right? Basically try to copy it.
Yeah, let's try. So copying, I mean, the only thing I know that is kind of close to copying is just to try to assign it like this. So now it's already lighting up here. What is IntelliJ telling me? Oh, wow. So X moved. Can we run this just to see the whole message? So this type, immutable reference to something, does not implement the copy trait. Thus, if you bind it or assign it to another variable, it's moving. And then if we move out of X, this is how you say it in the Rust world. You move out of X into Y. Thus, X is not there anymore, even though it looks like it is, but it's not. And that's why we see this error here. Interesting. So what I wonder though is, if this is not implementing copy, how does it work that I can do this? Like, why does X still exist after I give it to the function? Like,
well, I would guess because you're explicitly giving it a reference to it, right? You're not giving it the value itself, but you're just giving it the pointer to the value.
But that's the thing.
You're saying that it can change it.
That's the thing. I technically, like, whenever you see this, you give it that. Like, I literally give it the X, and if it's not copy, then it should go there. Like, this is part of what ownership means. That if something is not copy, you move stuff around every time you assign it, or you pass it as an argument to a function. So in theory, using it afterwards should not be possible, but it is. And I have a feeling even though I don't know how to prove it, honestly, that this is related to reborrowing. So can't I have, I don't know. I don't even know how to do it. I can't prove that, because here it seems to be copy. Maybe there's somebody who can leave a comment to say why that is. I think it's a feature because it would be annoying if it wouldn't be, if you would always consume your borrow, right? Just because you pass it on to a function. Even though apparently if you bind it, that's exactly what happens. Okay. So far we only dealt with these types where the ownership is a bit hidden. I mean, now for the first time we have an instance of that where we move something, and with these primitive types it's a bit hard. Mutable borrows, apparently they are non-copy, they are move. What does that mean for a, if we stay with this even longer, what does this mean for a shared borrow? Like if I have this z here and I assign it, let's make it y to z. Okay, so far so good, but what if I try to use it? I can use x, I can use y, I can use z. So multiple readers are fine. Apparently this one is just being copied into z or z, wherever you're from, but it's not moved like in the previous example. So this one moves.
Yes, because it's just pointing to the value and it's not modifying it, so it's fine.
Yes.
Yeah, that makes sense.
This also means that immutable or shared borrows are copy. You can copy them around. Whereas these ones, the mutable ones, they're non-copy. So you move them around, which makes sense. Then it's always this one writer that stays alive, or that one writer that you want to keep, and you don't accidentally spawn new writers to the same memory location and thus violate that essential guarantee that Rust makes or gives you. Yeah, wonderful. Okay.
So this is what happens in general when you assign, or when you pass in a value or a variable in a parameter. It either moves it or it either copies it, depending on what kind of value it is.
Very well said. Yes, that's the case. Except for here, where it kind of can't copy it, so it should move it, but it doesn't move it. It kind of just works, except for this. What's going on here? This is going on here. What's happening? What's this? Yeah, please.
Oh, so it's dereferencing it basically, and then it can copy it, and then it's making it mutable again. So it is doing a copy.
Is it doing a copy? Well, so in theory, right? We have this x here. We can talk about this for a long time. Apparently, it's a bit unusual, but there's a lot in it apparently in these borrows. So we have this 42. That's the memory location somewhere where there's a 42 in there, let's just say. And this is essentially a pointer to that 42. But we don't have pointers, right? We have borrows. And this, through that borrow, we allow mutation of that memory region. Okay. So if I dereference it, I don't automatically copy it. All I say is, okay, now give me what that borrow is pointing to. And because it's a mutable borrow, I am allowed to mutate that location if I wanted to. This is why this works. So there's no, I want to mutably dereference something. No. You dereference it, and if you dereference it through a mutable borrow, you can change it, otherwise you can't. And Rust knows the context. Rust knows that an add assign operation needs a mutable destination. Makes sense. So here now we essentially, after dereferencing, we see this 42 and we can change it. And then we dereference it again mutably, which creates a new borrow just for that, just in that case, just for this one usage. And Rust seems to be able to know that while I'm dereferencing this X, I'm not using that borrow. I mean, there's not two writers available. Rust knows that, because in theory, the X is kind of still there, but you can't use it anymore. You can't do anything. And then this freshly created mutable borrow moves in to this function, and it stays there. It goes there to die, so to say. But it's just a reference, so it's not really doing anything. It's just, oops, I don't know that, I don't point to that thing anymore. I'm gone, but the original is still here. Hence, I can still use it. And this reborrow is something that Rust does automatically in these cases. And that's one of the few occasions when something happens automatically, because Rust really forces you to be explicit. And that's cool, right? Because I'm pretty sure that's the explanation. If not, please tell me in the comments. Because I want to know what it is, but I think that's it. Because there isn't so much that Rust actually does automatically, and this reborrowing is exactly it. And yeah, I think it's cool that we're forced to talk about it just by looking in detail at what we see here and what that must mean. Nice.
Definitely.
See, this is what you get when you just talk about things sometimes. Then you get new insights, because I also wasn't aware I was just using it like this. And sometimes mutable references, they behave a bit odd, and then you just fix it because you learn how to fix it. But you just have a hunch of maybe not even that, why that actually is. You don't care, you just move on with your life. But this is why, and now I kind of learned something here. That's how it should be. Okay.
So did I.
And hopefully our viewers. Then let's talk about, or let's use this knowledge. I mean, how hard could it get? I think we are already through the hardest stuff when it comes to ownership and borrowing, just by looking at references. Let's try to bring in something new, which is a struct. Struct foo, because naming is hard. And yeah. Is this valid? What's this?
It's a type, right? You're declaring a type, essentially.
Yeah, I guess. I mean, I rarely use this, because what do these do? Like, what is the capability of this foo? Why would you have? Why would
remember the name? You get to choose the name.
You get to choose a name and have it in your program. Okay. It really can't do anything. But let's create a foo. Let's remove a few things here and let x be foo. Okay. And how can I use foo somehow? Yeah, sure, I can use foo. So let's see how it acts in terms of ownership and borrowing, I guess, right? Because that's the simplest possible struct. Like, literally, there's not much to it. Okay, what do you want me to do with foo?
What is there to do? I don't know. Maybe you can use it in the function.
Okay, I could. Let's just do that. Fn do foo. Ah, better. Kung fu. Huh? Okay. Kung fu fighter. Foo. Okay. Let's just do this. And then we do kung fu with X. And then do kung fu again. And it tells us what? User moved value. Okay. So foo, what does it mean for foo? What do we learn about foo?
Well, it behaves like the other variables, right? It's basically the same as we've had before.
Too fuzzy. Can you be specific about what the same means like before?
Well, about the moving and the copying. So basically now it's not being borrowed, right? It's being copied into this function. So if we were to pass in a reference...
Wording, phrasing? Are you sure it's being copied?
Moved.
Okay.
Moved into the function.
Yeah, exactly. Okay. It's moved here. First Kung Fu call is taking the X, it's moving X into Kung Fu, and that's where it goes. It doesn't come out of that anymore, huh? Okay.
Yeah. So it's taking ownership, and then it basically goes out of scope when the function ends.
Yes. And then we can't use it again. Fair enough. This also means that by default, structs are, what are they or what are they not?
They don't have the copy trait like we said before.
Yes, they are not copy. They are not copy. So I think we can derive kind of a little bit of knowledge from, we can derive from there, which is that by default, structs can do nothing. I mean, it's a bit of a jump right now, but I can tell you from my experience, that's how it is. They do nothing. They can't do anything. They can only move, even though with foo, you know, what's the benefit of it? I don't know. But yeah. How can we fix this? How can we let the second kung fu call use this X while it is not copy?
Well, you could return it back from the function, right? So the function takes it, does something to it, and then gives it back.
Okay. Kung Fu Fighter, it returns a foo, and we just pass the fighter here. And I noticed that while we do these sessions, we just gloss over or never explain any of the any of the syntax here. And it's just there, and people might expect this, right? Return fighter. Or might expect a semicolon here as well. But we don't do that in Rust, do we? Not so much. So how does this work? Like, I use semicolons here, right? So why can I just do this? No, I can't. Okay. I also can't do this. But here somehow I'm allowed to not use a semicolon. I don't have to do return, even though it allows that if I want to. What's this about? Yeah, maybe we just put a pin in this because it's a bit of a digression. Let's just focus on making this movement related stuff work. And then I guess I catch it here, huh? I bind it to something new or fancy as I am. Okay, kung fu. And that seems to work. And it does actually work. Yes, nice. Okay. And interestingly, I think most of Rust, if not all of Rust, would work just with that, just with with the movement of things. Because in theory, if you want a function to change stuff, you pass it in, you hand it over to the function, I give you the book, you do stuff with it, and then you return the book to me. Like, as a process. And then every function has probably a bunch of return parameters that, or return values, because it has to return a bunch of things that is passed as parameters in the first place. Yeah, and you can imagine that's kind of cumbersome, even though you can do it. And that's, I guess, is where borrowing was invented, because that's the kind of automatic way of doing this. Here, just use it, and it automatically snaps back to me like on a rubber band. That's how I envision it sometimes. Which also means that maybe the next level of this kind of this function here, yeah, can we get to the next level that doesn't have to do this dance?
Yes, I would say so. Then basically passing it as a borrowed value, right?
Yeah, let's just do it like this.
And then depending on what the function does with it, either to make it mutable or not mutable, but it has to be borrowed.
So then we don't have to do this anymore. We now have the rubber band. And we can just do this as often as we want, and it will work. Yeah, it does. Yeah, that's also something, huh? Rust has this built-in linter for quite a few things, and it will tell you when you forget things. And that's one way of fixing it. Just put an underscore in front, and then it should not complain about that anymore, that you don't use fighter at all. Okay, so that's one way of doing this. But foo, like how, why do I have to reference foo? Foo seems to be nothing anyway. It's more like like a marker. It marks something, its presence maybe, or lack. How big is foo in memory? What do you think? How much memory does it consume? How many foos can I have in a computer?
Well, it's a good question. I mean, the data it holds is basically nothing, right? I don't know if it takes memory to actually store the fact that foo exists.
Yeah, good question. Like how, if you put foo into an array, like, does this ever grow beyond a certain size? I mean, long story short, this is a zero size type, I believe, because it doesn't store any data. It's just a type at compile time. It's a marker. It's nothing more. It has no data. And what has no data is zero sized. And that has certain implications. But I think for us, it also means that there's nothing preventing us from making it copy. Like, why can't we make it copyable so that I want to do this. This is what I want to do. And in order to do that, you use something called an attribute. So this is the syntax for attributes. And you'll see this a lot in Rust programs or in the standard library or, yeah, in many places. Have you seen that before?
I have, and it always looked a bit like magic to me, because that's really what it is, right? You write a line above the struct, and then all of a sudden, it just works.
It just works, yeah. Yeah, that's true. It is magic because I mean, yeah, I mean, it's magic and also not magic, because to my mind, like the way that's my worldview here, because everybody must have their model in their heads in order to make life work for them, I guess. In order to make my Rust lib work for me, I see attributes exactly as that. It's metadata that you assign to all kinds of items that the compiler sees, and then the compiler can do something with that data. And in this case, it will implement. Oh, look at that. I can actually jump there. I can press Command B here. And I can jump to the standard library here in marker RS. And it shows me a trait that is copy. And that is empty. So it's a marker trait. And this trait, again, it does nothing except for marking something. Like, fix me. Okay. That's a standard library. It's okay. It's safe. Yeah, there's always a lot to be done, I guess. And this syntax means that everything that implements this copy trait must also implement clone. And clone is a trait that actually does something. It says, I have this clone method here, and given a borrowed, given myself as a reference, I create a new version, a new copy of myself. I clone myself, which I return. So I basically turn something that is borrowed into something that is owned. That's what clone does. And of course, everything that copies itself automatically in situations where that needs to be should also be clonable. And this is what that relationship signals here. And this is also why you have to derive both. You can't just derive copy.
I see.
Clone is not implemented for foo because it's required. It's a bound. So it's a constraint, if you so will. Everything that wants to implement copy must implement foo. And that's what the compiler does for us. So the compiler now literally creates a function somewhere that is clone. So I can, let's actually only implement clone, but not copy. We should be able to do that. And now I can try that function that we've just seen. So look, it's still being moved here. But now I can say, well, let's do a manual copy, right? Oh.
Okay. Yeah, I mean, I think that is the question that I had. Like, what is the difference between copy and clone? Because it does the same thing, right? But copy is then just the flag to tell the compiler you can do this on your own. You don't need my help for it.
Exactly. It signals even more. Like, not only is copying happening automatically, for instance, for primitive types or for shared borrows, as we have seen, but also it must be cheap, dirt cheap. It can't be expensive. For example, if you have heap allocations, vectors, strings, whatever, these are not implementing copy, because then you can just accidentally, without you knowing, right? It's kind of implicit. Look at this. It just happens. Oh. Then this is expensive. Look, now this passage of foo could be very expensive if this would contain expensive stuff inside of it. And this is why there's this differentiation. So copy is only implemented for types that are cheaply to copy or cheap to copy. Which also means that if you would pack something that doesn't implement copy into your structure, like a string, then copy can't be implemented because it's not implemented by all of the members of the structure. So copy is a transitive property that must be shared by all your fields, and so is clone. And this is what the compiler does for you. It just implements this automatically, does the boilerplate code, so to say.
Okay, so Rust kind of protects you from from making mistakes there, basically. So it wouldn't easily let you allow making a copy out of a lot of data, essentially, something that's not very efficient.
Yes. It doesn't work because that string just doesn't implement it. How should the compiler know how to copy that or to clone it if it's not, or if copy is not implemented? Strings can be cloned. So in theory, the compiler could just say, hey, you can clone it. So I just implement that. I just clone things because you asked me to, but the compiler does not do that, fortunately. So this is magic. Somebody just implements a method for you, and that's the compiler. And I think we can even make that magic visible. Let's see if we have some IntelliJ magic here. Show the result of macro expansion. Cargo expand. It does work. Yeah, I must have pulled in a lot of dependencies here. And some crates, they seem to be taking some time here to compile, but it's doing it. I'm also just doing this on a MacBook Air. Okay, so here's the result. Let's bring this full screen. And you see, this is what the second pass is that the compiler sees internally. So the compiler expands code. Okay, is this still what we wrote? There's main, and there's two mains now, huh? Rust C main. This is tests here. So this seems to be related to test. Maybe it actually expanded tests or something like that. This is our foo, like it was before. Some additional attributes that all of a sudden allow dead code. So this is, by the way, a way to pacify the linter. You can just allow certain things that the linter doesn't like if you want to. You can also deny it. You can do a lot of cool things with these attributes. I think we should dive into that at some point. But here, that's what we came for. There is our clone implementation for foo. And interesting, it matches on itself, sees it's a foo, and returns foo. So I think that's a kind of a complicated implementation of that, because you could just return a foo like we did before, but it doesn't. Yeah, anyway, in the end, that's all optimized away, and it doesn't matter how complicated it looks. It's free, essentially. Also here, all these additional statements that it puts in. Amazing. But yeah, that complexity is behind that if you are willing to look. Yeah, that's what the compiler does.
Does look a bit simpler though. I like that one.
Yeah, that one's much better. But it's amazing, like this complexity that's already hidden for you, that is just behind the scenes. But that's also Rust. It's the same thing. You could write it if you want to. It would be valid Rust at some point, I think, or to some point. All right, that's copy and clone for a structure with no fields. And 30 minutes in, I think that could be a good time to stop this episode and look more deeply into structures and more complex structures in the next episode.
Can't wait.
Me too. I think tomorrow it will happen. So thanks for watching, and we hope to see you then.
See you.
Bye-bye.